Check. All right, so back where I was, color wheel at its simplest. So let me blast through this. Everybody has to have, or not has to, please open up Photoshop. And I need to quit this so that I can get into Photoshop. So just a quick review in Photoshop again. If you click on either the foreground or the background color, it's the two icons. They're at the bottom of your toolbar on the left-hand side. Typically, they're black and white, but they can be any color. Once you pick a color, that will change. If you click on the color picker to open it up, you can actually see, I'm going to start off with red values. So I'm going to type in a value for my R. I'm going to type in 0. Hit the tab key to go to green, hit 0, tab key to go to the blue, and hit 0 again. And by definition, that is black. We have 0 red, 0 green, 0 blue. All three of those are black values. If we click on the radio button up in the top part of it where it says HSB, this stands for hue, saturation, and brightness. If you click on it, what you see is the column itself, the column that's next to this big field, this column that's got the two little arrows on it, always becomes what the radio button is that you select. So if you cannot remember what something is, let's say you cannot remember what hue is, well, that's what H stands for. So click on the H button and you can see the column then becomes all of the hues that are possible. If you can't remember what saturation is, you click on the S button. This brings up saturation. And then finally, back to B, which brings up the brightness of the image. If you take those two little arrows that are at the bottom and you start to slide them up, what you'll see is that the RGB values go up and they all remain equal. I have no color in this. This is a complete grayscale. This is a completely desaturated set of colors that we're actually looking at. But you can see as I go all the way up to the very top, I end up with 255 for my red, 255 for my green, 255 for my blue. By definition, that is white. If I pull this down to 128s, 128 is considered middle gray in Photoshop. Now, it's a little tricky because the truth of the matter is, and we don't need to get too deep into this, but nonetheless, if you take the distance from 0 to 256, 0 to 255, it is 256 values. However, half of 255 is not 128. Half of 255 is 127 and a half. That actually introduces a rounding error in Photoshop. It is impossible in an 8-bit image for you to have a true middle gray. It either goes on the arrow to one side or the other. It can either be 128 or 127. Photoshop decided it'll just call it 128 by definition. Once you start to get up into 16 and 32-bit, that changes, but that's another conversation for another time. So at any rate, if we click on the radio button that says R, we just get the R value, and you can see that this is now what the column is actually going to become as well. And if I click on it and start to drag it up and down, you'll also notice that the R value is also changing and the other two values are remaining the same. So it's just a way to go in and think about things and realize what the color picker does, but especially understanding that this column actually reflects whatever radio button that you actually click on it. Okie dokie, back into this. So again, don't let this word scare you. What is tristimulus? Tristimulus is all the colors of the spectrum can be described in terms of 3 values or stimuli. Again, this is based on your eyeballs. Your eyes actually see. There's cells in your eyes that are sensitive to red, cells that are sensitive to green, and cells that are sensitive to blue. And by using different amounts of nerve signal from those respective cells, you can see any color in the rainbow or any color that human eyes can actually see. Human eyes are tristimulus. They can be plotted in 3 dimensions. We're going to actually look at that in a second. However, and this is an important thing right here, they do not have to be 3 primaries. When we talk about primaries, RGB is red, green, and blue are the primaries in an additive system. CMY are the primaries in a subtractive system. HSB, hue, saturation, and brightness, which also describes color, are not primaries. So that's what this conversation, that's what this whole sentence is about here. Don't worry, you'll see it here in just a second. So what I need you to do is take a look at this, and what you should be looking at here, again, this is a two-dimensional screen, I realize that, but it's a three-dimensional illustration. It's supposed to be a cube. So can everybody sort of see this as a cube? And if you think about this cube, what they are doing is, again, you can plot that 0 to 255 on different axes. So if we look at this corner right here, it is the blue axis. If I start here at the very lower corner, here, I'll show, I can't, here, I'll do it on my screen here so you see what I'm ultimately talking about. This corner right down here, blue at that point is 0, and if I get all the way up to this corner right here, blue is 255. If I go over to this corner and actually click on this part right down here, this is red. It starts at 0 red here, and I go all the way to this corner right here, it's red 255. And then finally, if I go to this corner right here, and it starts at green, and green is 0, and all the way up to here is green is 255. So this begins to deal with color the way it really is. It's not a two-dimensional space like the color wheel. It is a three-dimensional space. We have 3 primaries. We are plotting 1 in each of the directions, and that will give us our entire color world. So you won't see this on the video. Actually, this will be tricky. I don't have my mic, so I'm not really sure you're going to be able to hear all this, but we'll go for the best we can. At any rate, if you imagine this room is a cube, don't imagine that it's wider or shorter. So just imagine that from the floor to the ceiling and out about here about the same amount, and then over here about the same amount, that it's a cube. Make sense? In this corner down here, we have 0, 0, 0 for RGB. That's where black is. If we go straight up the wall, we do not go out this way. We do not go out this way. We simply go straight up to the ceiling. I get 255 green. That whole line is a pure set of greens. If, on the other hand, I start down here, again, 0, 0, 0, I have a 0 blue, which is a black blue, and I run along the floor line right out here. I don't go up at all, and I don't come out at all. I just land at this corner up here. I have a pure blue there. And then finally, if I do the same thing, start here, 0, 0, 0, and go along this line along the floor out to its edge, that is my red axis. Again, I don't go up at all, and I don't come out into the room at all. Those are where my pure primary color lines are. However, if I go all the way up to the ceiling, that gives me 255 green. I come all the way out into the room here to this edge, that gives me 255 blue. Again, I'm right up there in the ceiling. But then I come over to here, in this corner right here, I have 255 green, 255 blue, 255 red. That corner is white. Opposite that corner, which is black. Where's middle gray? So right here in the middle of the room. Make sense? This color space contains all of my colors. Unlike the color wheel, which couldn't deal with lightness, this can. This has black, this has white, it has the whole range of neutral grays. It is three-dimensional and does not want to go any further. Hang on one second. Huh.
So sort of dealing with brightness, how bright should your computer be when you're out of range?
We are going to talk about exactly that today, and I'm going to show you how bright it should be. God, I hope this isn't going to just be techno day from hell. Well, but it looks like it is, so yeah. Nope.
Sorry,
Thanks. Oh, that's what ended up happening. It duplicated the slide. Okay, sorry. Okay, so this is that same three-dimensional cube that we were just looking at. If we do a cutaway of the cube, so I've actually removed part of the cube right here, and I'm just looking at where this point is right here. And you can see this gives me RGB values. I've got a red value of 51, a green of 153, and a blue of 204. And it makes sense because, again, the location of this is determined by the RGB coordinates. So if I'm looking at the amount of red, again, red is 0 right here at this corner. And if I come out just a little bit, which is where this one is, it makes sense. That's 51 out of a possible 255, right? So it's just a little bit of red in there. If I do the green part of this, 153, you'll notice the green value down here would be 0. The top would be 255. It's about halfway up, which is, again, 153. So it explains the amount of green. And then finally the blue, and the blue is going from this back wall all the way forward. This is almost all the way to the front. And again, that's why my blue is a 204. Does this make sense? The reason this matters is that until they developed this system, there was no way to talk about color in a way that you could convey color to someone else. If I said to you turquoise, what does that mean to you? Your turquoise is going to be different than mine. If I said to you light blue, yours is going to be different than mine. If I said pure red, it would still be different. So what they did was they came up with a system that no longer relied on using labels for color. What they've got now is a system that defines color by location. This location, 51 red, 153 green, 204 blue, in this color space is the same for everybody in the world. So I don't have to say, oh yeah, it's a little turquoisey bluish kind of green kind of thing, which means nothing to anyone. I can give you the coordinates of this in a location in space, and your color will be exactly the same as my color. So now we've defined color by location. Does that make sense? And that becomes critical. That's how Photoshop does all of its work, is color is defined numerically by a location is defined numerically. Okay. There is a unique point for each and every color. Color is defined by its location. Again, back to what I said earlier, it does not have to be primaries. This does not have to be RGB. HSB, hue, saturation, and brightness, are not primaries. I need everybody, if you're on Windows, you can't do this, but you'll see it on my screen. If you're on a Macintosh, I need everybody to do this with me. Go out to your Finder. Go to your Application folder. Go to your Utilities folder that is inside your Application folder. And inside that Utilities folder is a Color Sync utility app. If you could launch that for me, that'd be great. Once you actually get to that, there is a series of tabs that run along the very top. You don't want to pick the first one. You want to pick the second one that just says Profiles. Once you actually get Profiles, I'm going to collapse all of my profile parts over here on the side. You should have, you won't have anywhere near as many profiles as I've got because I got a lot of custom stuff in mind. But you should have a system, computer, user, and other on here. If you open up your system profile, inside of that, you should have a series of profiles, and the first one I want to look at is Adobe RGB. If you click on Adobe RGB, you will get a preview of what this color space is on this screen. Does everybody have this up? Did everybody get there? You want to get there? Did you find the Color Sync utility? Oh, so open up Utilities. Oh, you're there. So then you're looking for Color Sync utility. Yes. Do not hit it. There it's not hitting it. What? So did you go to your application folder? So let's try this. In your sort for your application, click on this guy right here. Come down this column.
Thank you.
And then again, don't hit repair, just click the second tab over. Okay, so, this looks like what? Anyway, I want you to come and hover your cursor right over the top of this and click and realize you can move this in three-dimensional space. So one of your assignments that's not written is to go home tonight, get really stoned and open this up, put on some Pink Floyd, and just do this for an hour. No, I'm just kidding. But what we are looking at here is a true graphical representation of the Adobe RGB color space. It is a three-dimensional space. If you orient it correctly, twist it so that you get the top of this X is on the white X is at the very top and the black X is at the bottom. What you can think of now is instead of that cube, imagine it really more as a globe, and that the North Pole, if we use the globe of our world as a metaphor, the North Pole at the top is white, the South Pole at the bottom is black. In the very center core of this world is neutral gray. On the very outside edges are the saturated colors, the most saturated colors that we can get. Does that sort of make sense? Check this out. If you go down on your list here, you can see down at the bottom you should have an sRGB. If you click on the sRGB, you'll see that your color space changes. Again, as you move it around, what you'll also notice is that it's not a globe, and the reason it's not a globe is that there are colors, certain colors that saturate much, much, much greater than other colors. So for instance, the distance from our center core all the way out to the edge of the green is much further than from that center core all the way out to where cyan would actually be. And the reason that is that because you can get more saturated greens than you can get a saturated cyan. So this is never going to be this perfect globe world. It's actually very sort of distorted and misshaped. And the reason it is that because of our ability to have those saturated colors. If you then come up to the top left-hand corner where it says the word lab plot, there's a little arrow that points down. If you click on that little arrow, you can actually come down and say, will you hold this for comparison? Because we want to compare Adobe sRGB with Adobe RGB. So I've now held this for comparison. You see it sort of ghosts out gray a little bit. Come up and click on RGB and on Adobe RGB, and you can see it totally swallows this space. So we can't do it in that direction. We have to do it in the opposite direction. So go back to that same little arrow at the top left-hand corner, click on it, come down and do clear comparison. And now we are going to then hold the Adobe RGB space. So back to that same little drop-down arrow, come down and say hold for comparison, and then click on sRGB. And what you can now see is how much smaller sRGB is than Adobe RGB. This ghosting that happens from these greens all the way out, that is all of that in Adobe RGB. All of those greens, all of those yellows, all of that stuff is a much larger space than sRGB is. And you can see it right here in color. Does this make sense? This is why it is so critical for you guys to have your edit settings set up correctly. You do not want to be working in sRGB. sRGB is a destination space. It's when you want to finally go out to your website. Again, the web is considered, sRGB is considered the color space for the web. But this is not where you want to be working with your master files. You do not want those in that small space. You want to leverage where all of these much, much, much larger colors, this bigger color space is. Does that make sense? Are there questions about this part? All right. So you can leave this whole thing open. Okay. What is hue? Can you tell me? We have color, but color is a combination of many things. So that's not an entirely wrong answer, but we need to be a little bit more specific. And so the best definition that I've run across it is this. It's the property of pure color that distinguishes itself from another pure color. It's what gives us red, yellow, blue, green. It's those phrases come from hue. Hue is defined by its location on the color wheel. We've already looked at this. Red is at 0 degrees, cyan is at 180, green is at 120, blue. You don't need to remember these numbers. I'm just trying to get you familiar with that part. If you now go to your color picker again in Photoshop, if you click on the H button, this column will become hue. And if you crank your saturation up to 100% and your brightness also up to 100%, you will actually see the colors reflected up in the top. So then you can actually drag this. These are all hues that we are looking at up at the very top. Now, we don't have to have the saturation and brightness cranked all the way up. The hue would still change, but it just becomes more apparent. It's easier to see. If we drop the brightness all the way down, then all of the hue changes in here. Actually, drop the saturation all the way down. Then when you go to do hue in here, whatever, you're not going to see any preview up at the top because we've actually said we want to see just the black versions of all those hues. So at any rate, that's why I keep these at 100%. Okay, you can leave that up for right now. Oh, sorry, go back. So in this illustration right here, if you look at these 7 patches along the bottom, the only difference here is the value of hue. Saturation and brightness are identical for all 7 of these. The only difference in this is hue. So what's saturation? Well, we've talked about saturation already in this class a little bit. Saturation is where you have one extreme as a pure color and the other extreme is a neutral gray. And the way you get to that neutral gray is by mixing an equal amount of complementary color, whatever that color is. Every single color in the world has a complementary color. So it's controlled by adding or subtracting complementary colors. Saturation is defined on a scale of 0 to 100%. 0 is completely desaturated, 100% is fully saturated. 0% saturation is a neutral gray. Do you feel like I've done this lecture before? Because I'm saying everything right before I put it up on screen. At any rate, in this case, these 7 patches differ only in saturation. The hue in these is identical. That's why it's misleading when you say hue is color. Because if you look at these, you wouldn't say, oh, those are all the same color. At one point, you get to completely desaturated, and there is no color, but that still has a hue of whatever this original thing is. It's just completely desaturated. So brightness is consistent in this. The only difference in this is saturation. Let me try again. Yeah. No, that's you had that look, and I'm going for it. Bingo. Yep, thank you. Thank Gia for me, please, or Cornell, whoever it was. Thanks. Okay. Brightness. This is actually the hardest one, I think, to define. Yes?
I just have a clarification on hue. So hue is just the 359 degrees around the...
Well, it's actually the full 360 because what they do is they do 0 and 360, both are defined as red.
Okay, but they do count.
They're the same spot. Yeah. But yes, no, it is strictly that. It's saturation and brightness are independent of that. That's where we're going. This is one of the hardest leaps, but you guys remember when I did the red car last week and how quickly that shifted? The reason I could do that was I had separated brightness from color. And then I was only changing one, and changing the color didn't have an impact on the tone or the lightness of the image. So anyway, brightness. This is, like I said, the hardest one. Brightness is the property of a color which appears to contain more or less light. Brightness is also defined on a scale of 0 to 100%. Every possible color appears black if its brightness is set to 0. It doesn't matter what the color is. If you set the brightness to 0, it will appear to be black. However, that's the way it appears to you. In Photoshop, it's still mathematically whatever that color is at whatever saturation that has had all the brightness removed. So Photoshop treats those as unique colors. Make sense? Oh, we'll take a look at it in just a second. You'll see. So in this case, the color is the hue is exactly the same. The saturation is exactly the same. The only thing that is shifting in here is the brightness. If we go back to our color picker in Photoshop, again, I'm going to set my hue to 0, which by definition is red. I'm going to set my saturation at 100, and I'm going to set my brightness at 100. I'm going to click on the saturation slider so that you actually get the column becomes the saturation slider. And if you click on the 2 little arrows and drag it all the way down, you actually end up with a neutral gray. However, it's not a middle gray, it is a white. Why isn't it a middle gray? Because brightness is controlling my gray values, and my brightness is set to 100%. So it is a neutral gray. It's just the brightest neutral gray you can get, which is white. If you click on the brightness slider and drag it down to the middle, which would be 128, or in the case of the percentage of the brightness, 50, you can actually see I get a middle gray. So removing the saturation changing the saturation does not change the brightness. Changing the brightness changes the brightness. Are we good on this part? It'll become a little bit more apparent as we work with this a little bit longer. So here, so how did they come up with this system? So what they do is they start with the color wheel. Again, we've already talked about this. Hue is defined by the location around the circumference of the color wheel. Saturation is greatest at the edges, and it decreases as you move to the center. And then the exact center is totally desaturated neutral gray. This is a 2-dimensional space, not 3-dimension. This is missing brightness. This has hue and saturation, but it does not have brightness. To get to brightness, you flip the color wheel. So here, this is, that's not going to, you flip the color wheels like this that we were looking at it. You flip it on its side like this, and you add the 3rd dimension. 3rd dimension goes up and it goes down. So in our case, the brightness element is now going up. In this case, I should just go through this and then read it. This is now a 3-dimensional color space, not 2. To create it, the wheel's laid on its horizontal line, and the 3rd dimension is brightness running from what I call the north, which is the lighter pole, to the south pole. I just use that as a metaphor. Again, hue is now still going around the equator of this, if we think about this as sort of that globe metaphor. Saturation is from the center out, so the center right here is completely desaturated. This area out here to this very edge, that very edge is the most saturated. And then brightness goes from north to south. However, look at the shape of this thing. I would have expected this not to be 2 cones. I would have expected this to be a cylinder. Why isn't it 2 cones? Why is the shape of that change? Think about it. As stuff starts to get lighter and lighter and lighter and lighter and lighter and lighter and lighter, don't you lose saturation? By the time you finally get to white, white is completely desaturated. White has no saturation to it. So the shape of that cone starts to come in because, again, saturation is the outside here. As the saturation starts to get less and less and less, all these colors are becoming increasingly desaturated, which means they are moving towards the center until you reach the point where you hit white, which is in the very center of this, just at the very top, maximum brightness, but no color. The same thing happens when you go dark. As you get darker and darker and darker and darker and darker, your colors get less and less saturated. You can see this in Photoshop again. So I'm going to do a hue of 0, which is red. I'm going to take the saturation and crank it all the way up. I'm going to take the brightness and crank it all the way up. Now, if we're only going to change the brightness value of this, I'm actually going to, I take that back, hang on one second. This isn't going to work the way I think I want this to work in here. Well, you can somewhat see it here. As we start to pull the brightness of this part down, you can see we've seriously lost saturation, and by the time we get all the way down, it's pretty much gone. So saturation is impacted by the brightness, and that's why that thing is shaped the way it is actually shaped. All right. We're getting there, guys. I swear this is not going to be the 3-hour lecture on color. We really are going to start to work on something. There was a really famous guy named Munsell who created this model. He was the first person to say, we need to get away from this RGB way of looking at the world, or the CMYK version of looking at the world. The CMY version of it was how painters painted for, 5,000 years. I mean, that was what they were using. RGB became more of an issue when we started dealing with light. But anyway, he created this model, and it is the model that we actually see today. It's what Photoshop uses. So in this model, what you've got is in the very center right here, you've got a column that starts black at the bottom, all the way up to white at the top. And then as we start to move out from this areas right here, our colors start to get more and more and more saturated to the point that we get out to the very edge. They are the most saturated at the very edge. And then basically the hue around this is the color wheel. It represents the whole range of hues. Again, he realized that you could actually have more saturated yellows in this. That's why this is pushed out further than this block of orangey that's right in here. The same thing, you can spot it over here. The cyans right in here are nowhere near as able to be saturated as the greens are. These push out considerably further. And it gives you this like really fucking weird shaped world. That's just the consequence of how color works. It's not, there's no magic in this. This is just, think of this as nature. It's why leaves on trees are not square. They're organic, and this thing is as well. Does this make sense? So with this color in mind, go back to your color sync utility. This is the model that is actually used for this. I'm going to clear my comparison again and just pick Adobe RGB. This is a Munsell model. Exactly what we were just looking at. Make sense? This is what Photoshop uses to deal with color. Okay. All right, we've already gone through HSB. Okay, I do want to take a quick look at this. So, LAB. We will get to LAB in a big way towards the end of this class, but I just wanted to point out basically what's going on here in LAB. In LAB, it's the same idea. You've got a color wheel that was actually flopped on its side, but the color wheel, unlike, just take a look at this really quickly so you can sort of see what's going on. I'm going to actually go back to the conventional color wheel that we were looking at first. In the color wheel, what happens here is that we've got 6 axes to basically deal with. We've got the cyan red, we've got the blue yellow, and we've got the green magenta. What LAB does is it gets rid of one of these, and then it repositions the other. So instead of having this cut into 3 different sections or 6 pieces of the pie, whatever, LAB just cuts it into 2. It's 2 axes. One of the axes is actually very close to this blue-yellow, and then the other one goes perpendicular to it. It just runs straight across here. So instead of having 3 coordinates determining color, I only have 2. I've got LAB stands for lightness, then the A axis and the B axis. The B axis is the easy one to remember because it involves the blue. It is the blue-yellow axis. The A axis is roughly the green. They call it green magenta. Sometimes you'll hear it called green red because it's not on this line. It actually runs much closer to like on a line like this. But then it's still flipped on its side, and the brightness is then introduced the very same way it is in the models we were just looking at. As you go up to the North Pole, it gets lighter. As you go down to the South Pole, it gets darker. But the advantage of this system is, again, in LEB, we have divorced the color from the luminosity. The luminosity exists all on its own, and then the color works on this AB scheme. Make sense? I'm not going to get in the rest of this part right now. We'll talk about that when we get into it a little bit later. Okay, that part's done. I've got one more part to look at really quickly, and then we are going to go to work. So, color managed workflow. How many people in this room feel like they follow a color managed workflow? You know, the people who go, like that, whatever, that's like being a little pregnant. It's either you do or you don't, or you are or you aren't. There is no like, kind of, part, a little bit. Anyway, no, there's none of that. So I'm going to convince you to go all in. How many people in here struggle with their color? Right? Yeah. It's how many people? Yeah. So I want to eliminate that. How many people here struggle with their exposure? Yeah. I don't do any of that. I deal with every single image I've done for the last 20 years. Perfect color, perfect exposure. Perfect. Not close to perfect. Not really good. Not almost. Not a little bit. And so I'm going to show you that workflow. I want to end that for you. For you guys to sit here and worry and think about color is pointless. Your job is to worry about making great art, making great pictures, doing whatever it is you want to do, but it sure shouldn't be the mechanics that sit underneath all of this. There's really smart people who've worked this shit out years ago. And the fact that you're not taught that at a much earlier stage drives me out of my mind, but that's just, the way I look at that, you're here now. And you're going to learn it now. Okay. So, the problem. RGB, CMY, HSB, all of these are ultimately derived from RGB. And as a consequence, they all have the same problems and limitations that RGB has. This is the key point of this part of this lecture right now. Every device, every eye, every sensor, every monitor has a slightly different definition of RGB. Your eyes do not agree on RGB. They interpret RGB slightly different. They are organic things. They're not cloned. They're not some digital clone of one another. They interpret color slightly differently. But our big issue is that monitors, cameras, sensors, printers, all of that stuff have a slightly different definition. There are an infinite number of these spaces. It just doesn't go on. Every single every eyeball in the entire world has its own unique space. Every printer, every monitor, every camera, every phone, everything. I mean, think about the trillions of things that we're talking about here, and they are all unique. That presents a huge problem for us because what we need in our world is consistency. We need to eliminate those variables. We cannot have this. This is an untenable situation. It is actually very easy to convert from one of these spaces to another. However, none of them stands out as the perfect thing for general use. So, device-dependent color. RGB values that produce the exact desired color on one device will produce a different value on another device. And you guys have seen it. You go into, Best Buy and you look at the wall of televisions and they're all showing the same picture, but they're all slightly different color. You guys are aware of this already. RGB values are monitor dependent. HSB values are also monitor dependent. CMYK values are printer dependent. So, how did they fix this? Well, there was a bunch of people who decided in 1931 they were going to go to Paris and try to deal with color. Now, if that was today, I would be on that plane right away. Let's go to Paris and just talk about color. Okay. What are we going to do the rest of the time we're there? We're going to eat really well. We're going to see some incredible entertainment. We're just going to be in Paris, one of the most beautiful cities in the whole wide world. Anyway, yeah, that's what we're going to do. I think this was a part of a perky business trip, but nonetheless, they did some serious work. So the first thing they did to try to establish this color, or to get around this color issue, is they created a person called the standard observer. So imagine, it's not just one person, it's one eyeball. That's what they've created. So they got all of these people together, hundreds, thousands of people together, and they took their responses to color, all these color tests, whatever, and they averaged them all together and said, okay, this person by definition is going to be the standard observer. And they defined color to that one eye. So now we've eliminated all the eyeballs in the world. We just say that, oh, my eyes see a little bit, my eyes are a little more sensitive to blue than the standard observer. My eyes see things a little bit more red than the standard observer. So that's the standard observer becomes this one thing that is the definition of color. Does that make sense? So that was the first thing they did. It was based on color matching experiments. This was the name of it. It's CIE, which it's French, and I don't speak French, so I'm not even going to try to go for that one. But this is the long and the short of it right here, and how this process works. This is the really important thing for today, because this will show you basically the process that we use to color manage everything. So I have got a file. So I've got a file up here that is a specific color. And these are the RGB values of it. So it's got a red value of 255, it's got a green value of 148, and a blue value of 21. You can actually create this color on your color picker. So if you go in your color picker, and I said it was a 255 red. Okay, who can remember the green and blue values? 148 and 21. Okay. So 148 green, and then 21. And that's the color that it actually is. Okay, so this is what my file is actually calling for. Okay, so the file is got those numbers. That's what it's calling for. I look at this file on my monitor. My monitor has not been calibrated, and my monitor shows me a very different color. It actually shows me a red value of 255, which is the same as the file called for. But look at the difference. In the green, it's actually showing a 248, and the file is calling for a 148. There's a big problem here. And then finally, down at the bottom, same thing with the blue. The file is calling for a 21 blue, but the monitor is giving me a 53 blue. This is an uncalibrated monitor. If I calibrate my monitor, it generates a profile, and what the profile does is it looks at the mismatch between what was asked for and what the monitor gave it. This is a color monitor puck right here. We're going to show you how to actually calibrate your monitors. How many people here are working on a calibrated monitor? Then there's 2 people in here who have decent color. Everybody else is guessing. How important is color calibration? People ask me this all the time. How often do you calibrate? I calibrate when my color is important. If you work for Pixar, you know how often you calibrate? You calibrate every day. And guess what happens if you don't? You're fired immediately. Part of the contract. You're not asked to start doing it again. You're simply fired. You're thrown off the team. You're out of the building. Why? Well, in Pixar's case, they do primarily animation. And so if a color mistake gets entered into anything that they're actually doing, and it finally goes to be rendered. Anybody in here do film, video? A little bit. So, well, anyway, rendering, basically you're taking the data of a Toy Story, and you have to render it to actually make it a real movie, to make it a real thing that you can actually then watch, right? Rendering takes forever. It's incredibly expensive. They have farms that just do rendering. They are just massive mountains of computers that crunch through all of this math. So imagine you're the person who's introduced a color error in that, and then they go to the rendering farm and they spend a month rendering the film, and there's a color error in it. That means they go back to the starting board and they start all over, and they fix the color mistake, and then they re-render the entire film. your rendering bill just went from $100 million to $200 million, and your time schedule just got fucked because now it's another month later and you're back behind it, and all your commitments to the movie houses have been broken, and you're under breach of contract, and they're suing you, and you can understand how important this is. So they just don't fuck with this. So at any rate, what the profile does is it looks at the mismatch. And so it's looking at the file, it's looking at what was asked for, and then this puck actually measures the color that's given. And so in our case, it actually says, okay, the difference in red, the file asked for 255, the monitor gave it 255, so there is no error that exists here in the red. In the green, it actually says, okay, the file asked for 148, the monitor gave it 248. We know to fix this, we need to subtract 100 green. That is the difference in 248 and 148. Does this make sense, everyone? And then the final value down here, the file asked for a 21 blue, the monitor gave it a 53. And again, the puck hardware, software combo realizes that to fix that problem, it needs to subtract 32 blue when this color is being asked for. Does this make sense? And then finally, if you put the monitor and the profile together, you will see that the red value being asked for by the file is shown on the monitor, the green value is also shown on the monitor, and the blue is also shown on the monitor. The corrected, calibrated, profiled version of your monitor now matches your file. And if you don't have it calibrated and profiled, like I say, you are simply guessing. You have no idea what your color is, none. And this creeps up on you people all the time. We talked last week also about the things that you wear, the color of the room that you're in. All of those have an impact on what your monitor is showing you. So the file and the monitor may be in sync, but you've got your bright pink t-shirt on, and that's actually throwing a pink cast onto your screen. You see that as pink in your file. To correct it, you start adding green. And the problem is that it's what you're wearing being reflected in the monitor, not a problem with your file. So your fix has gone into the file, and then you go to print it out and you say, well, fuck, it's too green. It's not the file's problem and it's not the monitor's problem. It is your wardrobe, it's your stylist's problem. Or your interior decorator. Are we good on this part? Does this make sense? Everything that we deal with in our color workflow system is going to be profiled. Everything. How many people in here have ever profiled their camera? You gotta be transfer students, right? No, just kidding. Okay. So profiles. Profiles are data that represents the color reproduction characteristics of a device. They are created by measuring the derivation, the drift from what is being asked for to what is actually being presented, what is being given. They allow you to adjust for that deviation. Profile transforms happen in a thing that they call profile connection space, or a PSC. We know PSCs as Adobe RGB, sRGB, ProPhoto RGB. Those are all conversion spaces. Working spaces is what Photoshop calls them. They don't call them conversion spaces, but that's what they really are. And again, by definition, this is a critical one here, they are device independent. My Adobe RGB on my computer is identical to your Adobe RGB, which is identical to somebody in Timbuktu's Adobe RGB. Everyone is device independent. And the advantage of that is that if we can get perfectly neutral color into that space, we can then actually get it out of that space, and that space has no impact on it at all. Don't worry, this will become easier to understand in just a second. So this is the holy grail of what we're trying to do. So if we take a look at this side over here, the left-hand side over here, you can do this for scanners, but most people now are doing camera stuff, but you can do this for scanners. You can profile a scanner as well. You take a camera and you shoot a picture, and you don't know if that, well, again, I can tell you right now, it's a device. It has got a dependency that we need to assign a profile to remove that dependency. So you build a camera profile, then you bring this into your input software. This would be either Lightroom or Camera Raw or Bibble or DxO or any of the processors that process raw data. You're bringing it into here. This profile has neutralized that color. It has removed its dependence on the device. It is no longer device dependent on your camera. It is the neutralized color that any camera that has been neutralized should give you. This gets brought into Photoshop, and this is where your working spaces are. The one that we use in this class is Adobe RGB. I strongly suggest you do not do your master file stuff in sRGB. We just looked at a reason why you don't. Is anybody in this room working in ProPhoto RGB? Most Lightroom to Photoshop workflows force you into ProPhoto RGB. The problem with ProPhoto RGB is it is a monster space. So if we think of Adobe RGB being like this, ProPhoto RGB is like this. It's enormous. You cannot describe that space adequately using 8 bits. You've got to go to 16-bit, which means your file size doubles. You are welcome to work in ProPhoto RGB if you want to, but you have to do it in 16-bit. Otherwise, what happens is that the way we look at it in 8-bit, those 256 tones produce what we consider to be continuous tone. You don't see skips in it. If you go to ProPhoto RGB space and you only use 8 bits to describe it, you get these huge spaces between your color. And so when you look at a ramp that should be a smooth color ramp, instead you get these chunks, these blocks. So again, if that's just a decision for you to make, but I'm telling you right now, if you try to work in ProPhoto RGB and use 8-bit, you will hate your life. You will get banding like you can't believe. And once you go down that road, you're fucked. So at any rate, I'm now here in this working space, conversion space. If I profile my monitor, I'm getting perfectly neutralized color. And if everyone in this room profiles and calibrates their monitors, all of our monitors will look exactly the same. Then by the same token, if you go out to your printer, you profile your printers. And again, no matter which printer you're working on, they will all print out the same thing. And they will be printing what your monitor has showed you and what you originally got from your camera, because this is a color managed workflow. Questions? We're going to come back to this slide a number of times. Last thing I want to hit on here really quickly is color temperature. What is it? You're photography students, you know you've heard color temperature your whole life. This is like hue and saturation and brightness. So, color temperature. It's actually an important thing in this whole calibrated workflow, because color temperature, actually we use it to define color casting. So the way the whole process worked was this. You guys all know what Fahrenheit is or what Celsius is. It's temperature scales, right? In the temperature scale in Fahrenheit, ice is at 32 degrees, boiling water is at 212. If you go to Celsius, 0 degrees is ice, 100 degrees is boiling. So that's basically the way it works. So what happens in a molecular world, not to get too physics here, but nonetheless, there's atoms inside of molecules. And if you add energy to that molecule, those atoms start to bang into each other quite a bit, whatever, and it creates heat. So that's the process. If we actually take water at normal room temperature and we start to warm it up, they start banging into each other, they start to agitate, and as it goes on, they finally reach 212 degrees. It starts to boil, and then it keeps going, because as it gets, that's what's actually causing the evaporation, is that the molecules are literally being knocked out of the water from all of this action. If you go in the other direction and you actually throw that same thing, that same water into the freezer, it starts to get colder and colder and colder and colder, and eventually it freezes and it becomes ice. So what you see is that there's the thing that we talk about with temperature is basically just energy. So there was a guy named Kelvin who came along and said, well, what happens if we just remove all the energy? That has to be an absolute. And it is. So there is a point where you can subtract energy, subtract energy, subtract energy, subtract energy to the point that you remove it all. It can't get any colder and it can't have any less energy than 0 degrees Kelvin, because there's no energy left. It's just, that's it, it's played out. In the Kelvin scale, that is 0 degrees Kelvin. This is also known as a black body. There's a whole set of names for what that would actually be. So you take this black body. There's nothing in the world, there's nothing in the universe that can be darker because it has no energy. There's nothing coming off of it. It's just this black void. It's not a void. It's a thing, but it has no energy. Does that make sense? Then you start to add energy to it. And as it starts to warm up, when it gets to be around 2,000 degrees Kelvin on this same scale, it starts to actually glow orange. As you continue to add energy to it and you get up around 3,200 degrees Kelvin, it starts to lose some of that oranginess to it, but it's still pretty warm. If you continue to go all the way up, adding tons of energy, you can get up into this 9,500 degrees Kelvin or more. The more energy you add, the more blue this will actually get. The 3,200 degrees Kelvin in this range right in here is old school incandescent light bulb in house. It's also what the photo lights in the studio that we use. Although those photo lights in the studio are actually 3,400 degrees Kelvin. It's only 200 degrees off, but they are slightly different. But it's considered a pretty warm light. The 9,500 degrees Kelvin right here would be the top of Mount Everest on a cloudless day with a really bright blue sky. It's really blue. This is also the color temperature that Macintosh ships with. Your laptop has got a really serious blue color cast to it. So do all these iMacs. The only thing that doesn't are like their studio monitors. So if you spend $8,000 at Apple, you can actually get a decent monitor. But if you really try to do serious work on your laptop, that's a piece of shit. So is the iMacs, even worse. So what do you do? Decent monitor, external monitor. Anybody wants to have that conversation, I'll talk to you about that. But at any rate, what you'll notice is that right here in the middle, at 6,500 degrees Kelvin, the blue cancels the yellow out. This is considered an absolutely neutral color. It's neither blue cast nor yellow cast. It goes right down the middle. So when we calibrate a monitor, we calibrate to this 6,500 degrees Kelvin because we don't want a blue or a yellow cast in our monitor. Make sense? Okay. Now would be a good time for a break. I've got 2 o'clock. Let's call it 2:06. Let's make this a hard 10. If you could be back at 2:16, that would be great. And we'll actually start doing some work. Are there questions about this? Yes?
Did we check out the color, whatever that thing
Yes,
is
the color calibrator.
on the media center?
You do, and we'll get to all of that when we do this. Yes? Oh, hang on one second. Let me just stop the recording.